Hello. You ready for an example problem? Couette flow with one wall moving? Let's dive in here. This is the situation. This wall is a static wall at the bottom, and this one at the top is moving with some velocity here, and we're going to call that U wall, the velocity of the wall. We like U because sometimes we use V for volume, but anyway. Down here we have a no-slip boundary condition, so the velocity ux is 0 at the bottom, and ux equals u wall at the top, of course, and we're solving for this flow profile. So ux is going to be some function of y. That's what we need to figure out. And we use this form of one of the Navier-Stokes equations in Cartesian coordinates. It's a steady state system. So that first term, the derivative with respect to t goes to 0. Nothing's changing with respect to time. We do have velocity in the x direction, but that velocity is not changing as you move in the x direction. So that term goes to 0. We don't have any velocity in the y direction, so 0 there. We don't have velocity in the z direction, so 0 there. We do have viscosity. Oh, and we did have density over there on the left-hand side. But we don't have any velocity in the x direction. It's the same question and same answer as the single derivative on the left answers the double derivative on the right. This term is the one we keep. So we'll write a big yes. We do have a changing velocity in the x direction. Velocity is changing as we move in the y direction. We don't have any velocity in the z direction, so that one goes to 0, or no change in the ux as we move in the z direction. And interestingly, we don't have any pressure drop here because this flow is induced by the moving wall and the viscosity that transfers the momentum from the moving wall down toward the static wall. And we don't have any gravity in the x direction either. We're assuming gravity would pull down, and this is flow moving left to right. So the complicated Navier-Stokes equation becomes quite simple, and we just have 0 equals mu d squared ux dy squared. That's nice. And of course the mu, we have a 0 on the left hand side, so we could divide both by the viscosity, and the mu goes away too. And we just have d squared ux over dy squared. Okay, so that's cool. Now what are we going to do with this? We need to integrate it. So we're going to integrate both sides. Integral of 0 is just 0. The integral of a second derivative is the first derivative plus a constant. So that's just going to be dux dy squared plus a constant that we'll call C1. Not to be confused with concentration, just a constant C1. And we can rearrange this a little bit, knowing that the C1 could have a positive or a negative, and it's still just a constant, so we can kind of move it on the other side and write it like this. And then we're going to separate and integrate. So dux stays on the left, and then we have C1 dy. Oh, I forgot my squared, didn't I? Oh, wait, no. I didn't forget my squared. I accidentally wrote a squared. There we go. So dux equals C1 dy, and we can integrate again. The integral of a derivative is just that thing that's inside the derivative, and the C1 comes out to the left, and the integral of dy is just y, but we do have a second constant, C2. Now we have our boundary condition number 1 that's going to play in here. We integrated twice, so we should have 2 boundary conditions, and we can say that our first boundary condition at y equals 0, ux equals 0. So plugging that into the above equation, ux is 0 equals C1 times 0 plus C2. I'll just write on the right hand side then that C2 then must be equal to 0. That's convenient. C2 just cancels out or just goes away. Then boundary condition 2 is that at y equals 2a, ux equals u wall. And so we can write u wall equals C1 times 2a. Oh, by the way, that's because this right here is the equation that we brought down after C2 went to 0. We can plug our new boundary condition terms into that equation. U wall is C1 equals 2a, and therefore we can write that C1 equals u wall divided by 2a, doing a slight bit of algebra. So if C1 is u wall over 2a, then we go back to this equation and we write ux equals u wall over 2a times y. And there we go. Now we have ux as a function of y. U wall is a constant. It's moving in a constant velocity. That's the reason we could get rid of our time derivative. And 2a is a constant as well. And now maybe we can just write it in here. Ux equals u wall over 2a times y. There's our answer.